Good afternoon, everyone. So today, there are a couple of lectures uh, today tomorrow. So what I'm going to start is basically some fundamentals on MHD instability, and the idea is that in this lecture, I would provide something like a physical overview. I think you have been doing a lot of computation stuff, looking at computational equations and so on. So this lecture in the next 20-25 minutes will focus on the physics part. So essentially you have been doing simulations yesterday of KH, but essentially how the KH forms, what is the physics behind KH is something what I'm going to talk about. And also I'll talk about the physics that you'll be doing in today's hands. So I will basically at the end of this lecture, I'm going to put a slide of hands-on. So essentially these are two exercise, two problems that you will have to do in today's hands-on. But you will know the physics, what is basically going on. So you will at least appreciate what is actually happening over there. Right. So the question is today Pallavi gave a very nice overview of MHD equations, waves in MHD equations, etc. Now, as you can see that the system itself is unstable. So she was talking about instabilities and so on. So let's see how these instabilities actually creep in. And point is that okay, the equations gives you instabilities, but do we see them in reality? Do we actually see them in action, in actual physical systems? So with this in mind, I basically would like to show some of the most amazing stuff in astrophysical systems. These are essentially very powerful energetic sources. This is basically a supernova remnant, which is called Tycho supernova. And you can see how nicely this structure is there. This blue part is essentially the X-ray emission. You have all sorts of instability, all sorts of turbulence basically going on inside this supernova remnant. Then, of course, this is a very classical coronal mass ejection, where you can see how the plasma is basically ejected from the surface of the sun. How is this ejected? What sort of process happens? And you know, sun is magnetized. So how you basically are able to throw the plasma, provide kinetic energy to plasma, convert it. Because essentially any form of energy will be converted from one form to the other. Then in doing so, some energy has to be lost, and some energy has to be gained. So what process goes behind this is what we'll talk about. And then you have this beautiful Cygnus agent. It essentially has a very pencil beam-like structure, but if you look closely into many of these jets, they are actually bigger. So why do these jets bigger? Okay, what is the reason behind it? These are cylindrical structures. Okay, you have a cylinder of plasma, you have a plasma cylinder, and then it is connected with another stage. They are bigger. So why they are bigger? Right? And then you have this beautiful crab nebula, which is essentially something which you have seen. And you can see how this crab nebula has these very beautiful filamentary structures. These filamentary structures, if you look closely, they are pointing downwards. What are those? Why are they present? Okay. So the question, so essentially all these astrophysical systems are completely made of plasma. And you can see all sorts of very detailed structures within these astrophysical systems. And the idea behind this is instability. Okay. So the question then comes is, how do you know a system? How do you build up a system in the physical sense? Like, for example, you want to, let's say, then you want similar of some region, fill you to give you a problem, use your favorite simulation code and simulate a check. What you will do. So essentially, there are different flavors of astrophysical fluid dynamics. And the first flavor is essentially in hydro system. So essentially, it's as basically a compressible invisible fluid. So invisible meaning it's not a viscosity fluid. About the viscosity and the non-ideal parts tomorrow. So essentially, it's a compressible fluid. Essentially, that means it's push them or provide a force, its density will change. Okay. So any force and density will react to this. It's a Newtonian framework, so all the relativistic. So it's very easy. You don't have to worry about Lorentz factors and frame transformation and so on. Then, of course, most important part of thermodynamics, and I think Anusha later on will just speak about some very important aspects of radiation physics, which is extremely important in these scenarios. So radiative process, and they also kind of govern the equation of state. So equation of state is essentially a relationship between the pressure and density via the temperature. So it's kind of connecting between this. It's like a closure equation to all sets of hydrodynamics and hydrodynamics equations. And of course, the most important aspect is what the focus of today's classes and tomorrow's is magnetic fields. So magnetic fields are present everywhere in astrophysical sense. Somewhere magnetic fields dominate the flow, somewhere magnetic fields are subdominant. But magnetic fields are present. Fourth system is plasma. You have ions and electrons called magnetic fields. Sometimes you have an environment dust. They don't couple with magnetic fields, but they interfere with the coupling between ions and electrons. So these processes are called ambipolar diffusion and so on. So there are up till now, what we have been doing is what is known as ideal, which in the sense like fluid infinite current. This is something what also already mentioned about. She also came up with this resistivity curve. We will come back again here. But essentially, you assume that there are no end of charge separations. If you immediately it will kind of get short, and you essentially have infinite current. Okay, so that is ideal MHD. But of course, this is not an ideal world. You have other sorts of dissipation mechanisms, and these dissipation mechanisms are the main culprit for producing sorts of instabilities that are actually coming. So this is like a dissipation mechanism. It gives you it gives some channel with energy, distribute energy in other channels like magnetic, thermal, so on and so forth. And finally, if you want to be more ambitious and do some more cool stuff, then you can of course add relativity, and that makes your life complicated. Sometimes it is very much required. Right. So now, since the topic is not instability, let us basically talk what is instability. This is a very basic principle of instability. So it's a very simple thing. You go home, take a bowl, take a pea, and put the pea on the bottom of the bowl, and you just what happens to the pea? क्या होगा एकदम धीरे से जोर से मत बनाओ बोल के मार के धीरे से मारेंगे क्या होगा it'll keep oscillating. So what is happening on you have given some displacement in one direction, but right, what is basically pulling it from? So there's a dispelling force that is gravity that is pulling it down. So it's just a slight thing. ठीक है अभी बोल को उल्टा put a P on that. Now give that slight tickle. What happens? Okay. There is no restraining force. So the force that is acting, the gravity is now form. So that means in the first case, the system is stable. What it means is that if I give a little perturbation, when the system comes back to its original form, of course the friction will, and then ultimately the P will come to that rest. But in the other case, even if there is friction, if you give a little bit displacement, it will essentially fall down. So if you have any perturbation and kind of undergoes a runaway process, it is essentially called instability. Okay. Now, in terms of physics, you essentially deal with potential energy. So potential energy, when do you say system is stable? Where is the value of potential energy? Right. So now what the idea is that because of the perturbation, you will have some change in the potential energy. Now, if that change is less than zero, then essentially you say that the system is unstable. Okay, and then there is a channel for your potential energy to convert into kinetic energy, and this is what happens. So essentially, in this case, when you do this thing, the change is negative. The potential energy gain, so when you force something, there will be basically falling it down over here. So this is kinetic energy, potential energy converting kinetic energy. Similarly, if you have a change in potential energy to be, let's say, greater than zero, then the system is stable. Okay, so this is essentially the case here. That the potential energy change in potential energy is greater than zero, and therefore, it will be basically coming to stable. So any kinetic energy will be converted to potential to kinetic, and then it just keep on oscillating, and then it comes down to its state. If you let's say if a change of if it is basically zero. Say for I put a ball on a flat plane and just put it down, right? So that's basically no change in potential energy. So that is essentially whatever you give input, it will just basically that much displacement. So this is called marginally stable systems. So right now, so this is basically the most simplistic of the basic instability. So now let us look at certain very simple examples of instability that we have encountered. And how do these instabilities actually play a role? And do we understand them physically in such systems? So the first instability, there is something which you have kind of experience in yesterday's class. Is the KH instability. I think you all have done that simulation. So the idea is that you have a layer. So what you had a box, you had a layer, then with velocity u1, u2, rho1, rho2, any density. You had assumed same density, but in general it can be any density. In general, you can also do gravity. Is acting downwards in general. So essentially, it's a very generic system of two layers either separated by which interface, and you have rho one, rho u1, u2 as velocity fields. You have a gravity acting along the negative direction. So now, if I consider the system, this is pure hydrodynamics. I've not included magnetic fields here. Okay, there's no magnetic fields here right now. There's no them today. So if I take this system, then I perturb this boundary. So essentially, I just put a wave, a little shorter wave. So essentially, what I'm going to do is, with my hand, I'm going to put this fluid blob here, so this fluid blob here, fluid, just like wave like this. Right? I'm going to do this. So let us assume this is X direction, this is Y direction, but I get you. No, what is happening over here is that in this kind of situation, you have when you push the fluid down here. Okay, so if then after pushing, if everything comes back to stable, then it is a stable equilibrium. Right? If I basically put down, then this disturbances go away, and then ultimately reaches something in the stable. But what happens is that because of this, you generate essentially pressure variations. And this pressure variation now has gradient of pressure. This is force which is a runaway fix. Okay, so now the gradient of pressure, if you look at it carefully, the gradient of pressure, so if I want to basically, so the idea is if you push this down, if I have a gradient of pressure which is going to push it up, then it is stable. But if I have a gradient of pressure which is going to push it down as well, then I'm unstable. Just like the gravity of that ball. Okay, gravity, because the gravity was restoring in one case, but gravity was actually destabilizing in the other case. So if you have such a situation, then I'm not saying it will be always unstable. There will be a situation when it will be stable and when it will be unstable. So how do you determine that when a system is unstable on what perturbation? That is basically governed by something called as the linear stability analysis, or the stability analysis that you do for any equation systems. So any perturbation is nothing but a wave. So how do you write a wave? I kx minus omega t. Basically just a simple equation for a wave where a is very small as compared to this thing. So it's just an amplitude of a wave which is very small, and you basically perturb this system. So if you now take this particular generic system, what you can do is you can actually do some very simple analysis, which is there in a standard textbook. You can even take the textbook by Honorable Chaudhary. There's a very standard derivation over there. And you can find out how this omega is related to this, the perturbation that you provide. That is the wave vector you provide. And omega is the angular frequency. Now, this relation is basically called as a dispersion relation, which relates, it's basically characteristic of a wave. Now, with this, you can compute, let's say, its phase velocity, its group velocity, omega by k is the phase velocity, d omega by dk is So you can speak about it. Omega case flows. But there's another important aspect that is basically hidden here. Is that if this omega is for some reason imaginary. Okay. So what will happen is omega is imaginary. There's an I line over here. So I times some I will become I square. There's a negative one. But there's a negative sign lying over here. So it becomes e to the power omega. So the wave, which was a vector thing, will now exponentially increase. That means it is unstable. Like what Pallavi also mentioned. So acha ye kab hoga? Where when it will be imaginary? This is the omega. When will it be imaginary? Yeah. Square root here. So इसको अगर square root करेंगे तो ये अगर negative होगा, then you take a square root, it's an imaginary. There'll be an imaginary component. So if this is more than this, then you are unstable. So there's a condition for instability. So this system will not always be unstable. Only that's unstable. Only when this is satisfied over this, then unstable. Okay. So now the point here is that, say for example, I keep the two velocities same. Will there be any instability? If I keep two velocities same, so let's say 2 is greater than 1. Even if I keep just two velocities same, will there be any instability? No? And rho 2 should be greater than rho. Right? Rho 2 should be greater than rho. And if I put no shear, then there is u1 or u2 में कोई difference नहीं. So ये तो zero हो जाएगा, और ये positive हो जाएगा, so then it's stable. Right? But let's say that I still put shear 0. But I put rho 1 greater than rho 2. Is it unstable? Yes. It's really balanced. Yeah. The dense fluid over a lighter fluid will go relativized. Now, when I put a shear such that it is, and the rho 1 and rho 2 are the same. If I put a shear, the rho 1 and rho 2 are the same, which you had in your pH instability. Will it be unstable? Yes. Which is so. Which is so. Right? It forms vortex. So it all makes sense here. Right? So if you basically can write this expression, see there's a lingering K over here. So you can find out what is the minimum K that's required in order to go unstable. अगर उसके K से नीचे डालेंगे तो unstable नहीं हो. Because there's a K here, right? So if you put the condition of instability, you can basically compute the units of this. Validity of the linear stability. Yes, very good point. So essentially the idea is that you want to set the onset of instability. And the onset of the instability is to begin with linear. First, when you basically start coupling modes which are generated, you start to go into non-linear phase. Then it does not work. But to initiate the onset of instability. Because you see, in the Bhargav's lecture also, she came up with this perturbation term, and then there's a perturbation. So she was negating it. Why? Because you are in this phase when the perturbations are slowly going, so small. So if the densities are constant, we have only shear velocity, then it doesn't matter what K is, right? Oh, yeah, so that is the thing, right? So then it grows at the smallest level. So then that is also another important aspect. So this is basically what the idea of KH instability is. So you can actually see the physics being displayed in your simulations. So now think about, let us basically, I will come back to this KH again, and you will do this again. Let us go to MHD cases. Okay. So in this case, there were no magnetic fields. So the force, restoring force or anything, had nothing to do with magnetic field. But now, if let's say in my system, magnetic fields are dominating the restoring force, then such kind of instabilities are called MHD instabilities. Okay. So let us look at an example. So you take a set of MHD equations, which you know very well. Ideal. Then you can do some stability analysis, linear stability analysis. I'm not going to do all the math here, but you can actually compute basically the change in the potential contribution from the plasma. And there are a few terms here I'll explain to you. So there are 1, 2, 3, 4, 5 terms here. 3 terms are positive and 2 terms are negative. The third term, the first 3 terms are essentially the plasma compression. So this is the pressure. This is zeta is basically displacement that you have created into the plasma. This is basically the something called the field line bending, and this is magnetic compression. Okay. So this is magnetic compression. This is curvature. This is the curvature. This is field line bending, and this is basically the magnetic compression. So you have the plasma compression, you have the magnetic compression, and the field line bending. All these three terms positive. So they're stabilizing, always stabilizing. Because delta W, remember, original basic physics. Delta W has to be less than 0. Now there are 2 terms which are essentially kind of what you can say, destabilizing. One has this gradient of pressure, and therefore this gradient of pressure will determine this. Therefore, pressure-driven instabilities. And then you have a parallel current, which I call the current. So he is essentially, I would call of B, and so they are essentially called current driven and pressure driven instabilities.
Everything inside the all the terms are inside the integer.
Yeah. But if this thing dominates, then it will be all negative. So that's the idea. So you have current driven and pressure driven, modes of instabilities. So let us look at some examples. So the first simple example is something which you have studied. I'm sure that you have heard about Schwarzschild criteria, like I mean, how the stuff basically transports conductive nature. So now let us think of it in a magnetized context. So essentially, you can think of like basically like a ball of plasma or a turbulent sheet of plasma. Sheet of plasma, and you are kind of having like a magnetic field on top of it. So again, this kind of situation, there's a slab of plasma, and yeah. So now the idea is the magnetic field of plasma. You do the same thing. You put a little bit of magnetic field and pinch it. Now, what will happen? What will happen? So if you do this kind of situation, you see there will be something called as a buoyancy force which will be acting. Okay. So there are 2 kind of forces, 2 kind of pressure. Inside the magnetic field, the pressure of the plasma is the magnetic pressure. It is essentially giving us p square by 2 mu naught or p square by 8 in Gaussian units. And the pressure, the gas pressure, the pressure of the gas. The external, there is no magnetic field. So it's only the external pressure, gas pressure. These 2 will be equal in equilibrium. In equilibrium, they will be all equal. Now the question is whether the equilibrium is stable or unstable. So the way to do this is you just pick up a little bit of a portion of plasma, the magnetic field will be dragged along with it. So you get this kind of a problem. So now what happens is that there is a density change, and this density, and there's a gravity acting. So basically there's like a buoyancy force which is given by this delta rho times g, which is e square by 8 pi h. So this will keep on this buoyancy force. So it's just like basically taking a ball from your water, basically. It's just like this. And the h, the scale height is basically dependent on the universal gas constant R, temperature T, and the acceleration gravity T. Right. But then you see, magnetic fields are like rubber bands. Basically, you must be playing this rubber band, throwing the rubber bands at the paper chain, right? So if you pull the paper chain and the rubber band comes back, when it comes back, tension force. Exactly. So magnetic fields also plays a tension force. So if you pull it out, your magnetic field acts as a tension and brings it down. Okay, so it doesn't like any of these changes. So you are kind of pulling it out. So buoyancy is kind of causing it going upwards, but then magnetic tension is kind of pulling it. In the case when the buoyancy wins over the tension, you are unstable. Because it will just keep on rising, and it will go away. Okay. So if a case comes when the buoyancy force exceeds the tension force, then you will go away basically. And this is something what is essentially known as Parker instability. And this is basically seen in galaxies. You see, if you take a sheet of a galaxy, you have magnetic fields on the galaxy. And it basically goes Parker unstable. So you will have local collections of high densities as stars are formed. Exactly. So these are Parker instabilities. And Parker instabilities, that is there. The question is that this perturbation, you see, when you bring magnetic fields into account, magnetic field is a vector quantity. So it has directions. So also waves has direction because it's a wave vector in magnetic field vector. Now we have to see in which direction the wave vector and the magnetic field vector are going. Okay. So if I have, let's say, a wave vector K, so this direction, I perturb my wave in this direction. Okay. So it will still modify the structure of the magnetic field, but this can give rise to what are known as interchange modes. And this is something you will do. They are essentially magnetic relative instabilities. So essentially, you are perturbing this thing, and it's called magnetic relative instability. They are called interchange modes. There are other modes. For example, if I have magnetic fields along this direction or this direction, and I basically put my wave in this direction, same along with the magnetic field. Then I have something called as undular modes. These are Parker instabilities. Undular modes. So, and then you can always have mixed modes and so on and so forth. And put your theory in any oblique direction, and you have all sorts of modes coming into play. You can do all sorts of things. So, but only thing is like your buoyancy force should overpower the tension and the gravity. So, if that happens, then we're unstable. Right? Second instability, I'll just take maybe 5 more minutes, if you can. So, second instability, which is I think very important from the perspective of jet physics, is essentially instabilities that are pertaining to plasma columns. So, essentially, you can think of a plasma column. So, if you take a plasma column, you essentially have pressure. That is the gas pressure, which is kind of like plasma column, magnetic fields. Magnetized plasma column. अगर ये दोनों pressure equal हो गया, so then they are kind of stable. Okay, so I put a toroidal magnetic field, or basically what I can do is I can put a plasma column and pass a current through it. IZ. So IZ will basically create a E5 magnetic field. Simple. Now the question is that okay, this is done. So I have a E5 magnetic field, and initially it's in equilibrium. So essentially the pressure, the medium of pressure force, which is mostly acting outwards, will be balanced by J cross B. So that is a Lorentz force. It is basically pushing inwards or upwards and so on. And as Pallavi also showed, that the J cross B can be broken into two. One is the magnetic pressure term, and the other one is which can be coupled to the gradient of the gas pressure, the tension term. Okay. So then, this is the equilibrium. Now, what happens is if I squeeze plasma some point. So what is going to happen? What if I squeeze this plasma? That's it's not really an equilibrium, but I just caught up and squeeze it. What will happen? So what will happen at the place of the pressure inside will increase. What will happen? Right.
Even in the case of flux.
So this is all ideal. So there is all the flux is conserved and everything is conserved. So if you just
There is outside pressure.
there's an outside pressure, but essentially when you pinch the magnetic field, your magnetic field tension and increase. Okay, so your tension, so because you have kind of reduced the small area. Okay, so the tension force, remember there is a del term here, so it is a 1 by r term. So if you reduce the radius a little bit, the tension will increase and the tension force will increase. So it will further push it down. Because the tension is kind of like a rubber band, it's like constricting. So it will further push it down, and push it down, and push it down. Whereas on the outer part, what has happened is that it has expanded, Like the next point, because pressure is dominating, and the point here is that the tension force has lost its balance. The tension force has lost its balance. In radial, we are talking about, because now here the radius is larger, so the tension force is much smaller. So the pressure overpowers your tension force. So here, total pressure overpowers the tension force. Over here, tension force overpowers the pressure. So you basically generate these kind of pressure regions. Okay. Similarly, if you say, let's say you take this plasma column and then you shift it from its axis. So what happens here? So here you can see that the magnetic fields are kind of spread out. Here the magnetic fields are kind of narrow. So again here you will see that there is a stronger kind of tension or pinch force which is acting because the magnetic fields are close by. Right? So you basically tend to generate more and more tension. Whereas here the magnetic fields are more open, so they are kind of lesser and lesser tension. So it will basically be giving you this S-shaped kind of kink-like structure. So if you just kind of quantify it will still do such kind of thing. So there are ways to stabilize this. If you put an axial magnetic field, it kind of stabilizes. But if you take a component magnetic field, these are the main instabilities that actually come into play. Okay. So now I have almost overseeded it. I think I will just give a brief kind of introduction to what we will be doing, what I'm going to teach in the next class. So, one equation that is very common is essentially the induction equation, which understands the evolution of magnetic fields. Now, this is something which you have known. Del V by del T is curl of U cross B. This is something which you know. But you have antidisciplinary effects, which I will talk about in the next class. And then you essentially also what Pallavi pointed out, there is an extra resistivity. It's like resistivity. There's legally it's basically a obstruction to a flow like this structure. So the obstruction of plasma flow or plasma flow diffusing from the magnetic fields. Essentially, what you would expect that the magnetic fields plasma is kind of fractional. For some reason, plasma diffuses out, kind of detaches out from the magnetic fields. Then you essentially have this kind of term here. Okay? And each of this process has its own time scale. Okay? So now the idea is that if you have two oppositely directed magnetic fields become close to each other, what happens here? So our 12th standard textbook says that magnetic fields cannot be connected with each. That's what 12th standard textbook says. But that's not true. So the physics happens at micro scales. In the micro scales, you essentially have two diffusion regions, which are called electric diffusion region, which is small, equivalent to its Larmor scale, and ionic diffusion region, which is slightly bigger because the mass of the proton is big, or ion is bigger than the electron, so it's much larger. In these scales, what physics happens. And here you basically have electrons drifting out from the magnetic fields, ions drifting out from the magnetic fields, because essentially it's too over there. So there are too many electrons and too many ions here, so they kind of have an interaction with each other, Coulombic interaction, which can kind of provide a resistance to your flow of electrons, and therefore it will go away. And one can then, so the idea is that the flow. So if I have a let's say electron, this point here, it is basically just do this thing. There is no resistivity here. The resistivity is far more formal here. So the higher magnetic energy now gets converted into kinetic energy and heat. So it pushes the plasma on this direction, and also it gets heated. Okay, and the physics is much more complicated. We'll discuss about this in the next class. But the idea is that you can find out the rate of such reconnection, how efficient it is. And the standard theory is of Sweet-Parker reconnection, which is the most basic of all. It says that it goes s to the power minus half, which is s is nothing but the length of the sheet times the Elfman speed divided by the resistivity. And Petchik goes as ln to the power s to the power minus 1. 1 by lawrence. Okay, so that's what the reconnection things are. I'm not going to prove all of these, but I think this part, perhaps you can do this if you can actually do your simulations very well. Okay, so this part you can prove this thing. Now, the idea is a corollary of Sweet-Parker reconnection. The idea is that Sweet-Parker reconnection is very slow, but if you increase your Lundquist number, that is S, to large values, which is typical of astrophysical systems. So, in numerical sense, if you increase your Lundquist number to let's say 10 to the power 4 or more, you see something amazing. You basically see what are known as steering mode instabilities. So these are essentially, this is like a normal plasmoid that you will form, and you will also form these mini plasmoids. Okay, so I have put in a movie in the Teams. You can have a look at it, how it evolves, and this is done with Pluto, right? So you can essentially do all sorts of things with Pluto, but and this hands-on would be essentially focusing on this aspect, that is essentially the current sheet aspect. So this is a classical current sheet. So essentially your magnetic fields in one direction, and in other directions, just like KH. You have classical current sheet. The idea is that you need to produce something, well, it's two current sheets. So you can essentially produce some features like this. So you can produce such kind of images from your simulations today. And if you are very bold enough and can do all sorts of fun stuff, then you can change the resistivity and run your simulations, and then can compute the reconnection rate and show this Sweet-Parker reconnection. And that's something beyond is there. But essentially, this is what I'll do. This will be displayed in the hands-on. So I'll stop here. I've already taken 10-15 minutes more, but I think we will stop here now. Is there any questions?
Was rate of
It's the reconnection rate.
reconnection rate. So it for Sweet-Parker depends on 1 over square root of S.
Correct.
You said if we increase S,
Yes.
then we can.
Yeah, so till 10 to the power 4, till the critical thing, it will go as 1 by S or S, and then it becomes stable.
If you increase S, the rate will decrease. Because 1 over square root of S minus.
Yes. So yes. So you basically decrease. So if you increase, so you go like down like this.
Then you have to decrease this.
Yes, and then it kind of so decrease S means increase change and state.
Reconnection will happen only because there is plasma going along with the field lengths. If there was only field lengths,
No. It's basically what happens at the so this happens at this diffusion region. What happens is that in this diffusion region you have many collisions of the electrons. So essentially now the electrons are not kind of stick to the magnetic field. So they can basically get disturbed from the magnetic orientation and move away. So resistance means it's paths may there's a resistance to move in its positional. So if you break that thing, then the electrons will move in some other direction. And that's why you see the magnetic fields kind of breaking out.
In sort of late time limits of the sausage instability, would we expect the column to sort of break off into different parts?
You basically see formation of these knots, some high density structures, and then it goes into non-linear.
We can observe them with
Yes.
It is written here that heat instability is correct.
Yes.
Helical kink is also correct.
Which one?
Helical kink.
Yes, helical. So helical kink, I can tell you, helical kink is slightly more stable than toroidal. Helical meaning you have a toroidal component also. That is a stabilizing component. ये है ना field bending, ये field bending and field compression. They are stabilizing component. ये field line bending है ना. Essentially, what is happening is that so if you basically just turn it, so already inherent tension of the field line bending, so it's a stabilizing.
So, there is something called Shukla bracket.
Yes. So Krishna, so this is mainly due to magnetic compression. So that is something which is there. So this is actually a Krishna's Shafnau complicated name. It actually comes from this. So you can basically do these kind of things from the idea is essentially the same here, that what dominates. So it's essentially from this the criteria comes out that when your system will go unstable and when will your system go stable. So basically, the criteria comes from here. So this is essentially the whole derivation process.
We have to in Tokamas we have
Exactly.
parallel fields.
Yes.
So we have to maintain that
Yes.
criteria.
Yes. And that is basically derived from everything is comes boils down from this is very basic. This is very fundamental.
Understand Bhargav.
Thank you.